The first section here that we're going to talk about are sectors and arc length. So sectors are a region bounded by sides of a central angle and its intercepted arc. So the sector area is kind of this yellow area here that we have. Um, I always kind of think about it as like a pie, like all that you're eating in that pie or that pizza, that's the sector area. So in degrees, hopefully y'all remember this formula. So if you're given an angle measure, you're going to take a fraction of that full circle, so that angle measure being in degrees, out of a full circle that's 360 degrees. So it's a fraction of the area of a circle. Well, the area of a circle is pi r squared. So that's the formula you should know from geometry on how to find sector area given an angle in degrees. Well, what about radians? Well, radians, we usually like to use the letter x instead of theta. Theta is usually dedicated to degrees. Well, if we're changing this to radians, we know that 360 degrees is the same thing now as 2 pi. So what ends up happening here? Well, the pi's end up canceling out, and instead of seeing it as x over 2, I'm going to rewrite it as 1 half x, which represents the radian measure. So again, radians are, it's kind of like an angle measure. So it's that number r times r squared. So either remember how to derive it from the formula you should already know to this, or memorize it. 1 half the radian measure times r squared. The arc length is to measure the distance along the edge of the circle. So here from B to C, that crust, you can say, like I always refer to it as a pizza crust. So this is a fraction of the circumference. So in degrees and arc length, we usually use S. In degrees, it's this angle measure that we're given out of the full circle of 360 degrees times the circumference of the circle. The circumference of a circle is 2 pi r. So that's the formula you should know from geometry on how to find arc length. So how do I change it to radians? Well, again, I'm using x to denote radians now. 360 degrees is 2 pi. So if we multiply that by the circumference, how do I simplify? Well, the 2 pi's cancel off. So really the arc length is the radian measure times the radius of the circle. So remember that we talked about in the radian lesson, if we're talking about the unit circle where the radius is 1, then the radian measure is equal to the arc length. But remember that radians are supposed to be kind of angle measures, not the arc length. Well, what if we're trying to solve for the radian measure? Well, if you divide both sides by r, you take the arc length and divide it by the radius. Now, you could also solve for the radius by doing the arc length over the radian, but we don't use that as often. But again, you can manipulate that as many ways you want. So just, again, either know the derivation, how do you go from one to the other, or memorize the formulas. Okay, K being sector area is 1 half xr squared. The arc length is the measure the radian measure times the radius. All right, so let's get some problems and let's practice it. So find the sector area given this angle measure and the radius is 2. So it's going to be 150 degrees over 360 degrees times pi r squared. Well, 150 over 360 reduces to 5/12, and then 2 squared is 4. And if we reduce that, we end up getting 5 pi over 3. And units are always important. So centimeters squared, since we're talking about area. Well, what if we're given it in radians? So again, the theta, probably change it to an x just to stick to that notation. So sector area for radians is 1 half the radian measure, which is pi over 5, times the radius squared. So there's a couple ways you can do this. I can change this to pi over 10, and this is 100. So we end up getting 10 pi centimeters squared. Again, because it's area. Area should always be unit squared. So make sure to include units where appropriate. If they've already included the units in the blend quizzes or warm-ups, make sure to don't put centimeter squared, centimeter squared. All right, let's practice arc length. Well, arc length is a fraction of the circumference. So it's 80 degrees over 360 because, again, a full circle is 360 degrees. And the circumference is 2 pi r. So 80 over 360 reduces to 2/9, and this is 8 pi. Well, it ends up just multiplying out to 16 pi over 9 centimeters. And we're talking about a length, so we don't put squared on our units. All right, this next question is asking us to find the arc length if the radian measure, so this is the radian measure, and the radius is 4 centimeters. So how do I figure out arc length? Well, arc length is the radian times the radius. So it's literally just going to be 1/8 of 4, which is 1/2. And that is literally, forgot the units, 1/2 centimeter. So that is the arc length of a radian measure. That's 1/8 and a radius of 4. So now we can always go backwards. Given a sector area is 12 pi, well, again, sector area is k, and a radius of 3, you find the angle of the intercepted arc in radians. So we're going to have to use the radian formula. So that's going to be 1/2 the radian measure x times r squared. So we'll end up getting 12 pi equals 9/2 x. Well, you can solve this in any way that you want to. I'm going to multiply both sides by the reciprocal of 9/2, so that I can simplify this fraction easier and just get that this is 8 pi over 3. And that is my radian measure. So again, knowing the formula, plugging it in the correct information, and getting your answer. The next one, given a sector area of 20 pi, so k equals 20 pi, and a radius of 2, find the angle of the intercepted arc in radians. So again, same formula. 1/2 times the radian measure times the radius squared. Well, 1/2 of 4 ends up just being 2, so then we end up dividing both sides by 2 and get that our radian measure is 10 pi. So here's another problem where we're given an arc length, the radius, and they're asking us to find the angle of the intercepted arc, which is the radian measure. So again, our kind of formula that we need to memorize is the arc length is the radian, which we don't know, times the radius. Well, they gave us the arc length is 29. We don't know the radian measure, but we know the radius. So we divide both sides by 10 and get 29/10. If you're the kind of person that wants to put this in decimal form, that's fine. You can put 2.9. And remember that radians are unitless, so you do not need to put units on here. You just box your answer, and that's it. All right. In the play posit, I'm going to have a question for you to answer these. All right. Hopefully you got those correct. These were unit circle questions, so you should kind of know those. The next question here is asking us to evaluate and put these into 4 decimal places. So I'm going to reset my calculator off screen. And one thing you should know about these is there's no degree symbols. Is that a typo? No. If there are no degree symbols, then these are radians. And especially with this one at the pi, you should notice that like if it has a pi in it, it's a radian. Okay. So these are all numbers. So these are all radians. So we need to make sure our calculator is in radian mode. Again, make sure you go to mode and you have the black box over radian or however way you change the mode. So we're going to do kind of like what we did before with degrees, where I'm just going to type it into my calculator and make sure that you round. So we get negative 0.6570. Well, cosecant is 1 over sine of that. Remember that if we're not doing the inverses, you should have the fraction on the outside. And then secant is 1 over cosine. And we don't flip the angle, we're just going to leave it as pi over 9. and we end up getting 1.0642.
All right. So I don't know if you've seen me record a video yet with a graphing calculator, but I wanted you to kind of see what exactly I'm inputting and showing you what your calculator should look like. So these are just examples of plugging in. There's no inverses, there's nothing like that. So just sine of 7 pi over 5, which again, 7 pi over 5 is just an angle measure. So we're going to make sure our calculator's in radian mode, which we go to mode, do that, sweet. And you just literally type in set or sine. And if you want to be very particular about your fraction, you can use your fancy fraction. Oops, didn't push the alpha hard enough. Y equals and press enter. And you get 7 pi over 5, which in this case you don't really need it, but it's going to be helpful sometime in the future that you know what's in the numerator, what's in the denominator. So you get negative 0 points. We're still doing 4 decimal places, so 9,511. Cotangent of 1.5, 1.5 is still an angle measure. It's a radian. So we don't have a cotangent button, so we're going to do 1 over tangent of 1.5, so in radian mode. So we get 0.0709. And then cosecant, again, we don't have a cosecant button, so we're going to do 1 over, not 11, 1 over sine of pi over 8. And again, don't really need a fancy fraction. You could do that for both of those, but you should still get the same answer as 2.6131. Again, make sure that you're putting this in the calculator with me so that you understand how this works. So back when we talked about the unit circle in radians, we talked about how we could find two angle measures using those exact values. But in these four examples, these decimals are not exact answers. They're very rounded values of radian values. So just like what we did in degrees, we're going to have our formulas for sine inverse, cosine inverse, and tangent inverse, where sine inverse, we get the calculator value and its supplement. But since we're talking about radians, 180 degrees is now pi. Cosine inverse is plus or minus whatever the calculator gives us. And then tangent inverse is going to be whatever the calculator gives us plus not 180 n, because 180 is degrees, but pi n. So make sure that when you're doing this on your homework, quizzes, tests, show your work. Don't just type in n or write down your answers. So now let's just type this in the calculator. So cosine inverse of 0.27. Well, what is this? 0.27 is the ratio. Plugging in cosine inverse of a ratio gives us an angle measure. So this is going to be our angle measure in radians x. So 1.29, or actually 297 rounds up to 0.30. But the rule for cosine is that it's plus or minus. The directions tells us that our answers should be between 0 and 2 pi, which 2 pi is about 6.28, including 0 but not including 2 pi. Well, positive 1.30 is between that range, so sweet, that interval of answers. But in order for us to change negative 1.30 degrees into an angle that's between 0 and 2 pi, we have to take negative 1.30 and add 2 pi to it to find the coterminal angle. So I'm going to literally do plus 2 pi and get 7 point, oops, forgot to do the negative version of it. So I'm going to do negative, I'm going to go copy and paste that and add 2 pi to it. Why did I kind of go back there? Like, why did I figure out that I made a mistake? Well, 7.580, whatever that is bigger than 6.28. So I knew something was wrong. It was bigger than 2 pi. So I forgot to do the negative version of that and do 2 pi to that and end up now getting an answer that's 4.99. So those are our two answers, 1.30 and 4.99. Now, how can I make sure that this was right? Well, these are our angle measures. So if I were to go in and press cosine, or I have to go down here. So cosine of 1.30, is that pretty close to 0.27? Yeah, if you round to the decimal places, it is. What about cosine of 4.99? Sweet, pretty close. So why wasn't I doing inverses here? Well, because 1.30 and 4.99 are both angles. The 0.27 was a ratio. You plug in ratios into inverses and get out angles. What about secant inverse? Well, again, just the same thing as we did for degrees. In order to plug in secant inverse into the calculator, what I need to do is take the reciprocal of this. So what I need to do is take the reciprocal function and the reciprocal of the ratio, which is 1 over 1.16. This is something that a lot of people try to do 1 over cosine inverse of 1.6. And if you do that, it might work some of the times. It might not. If you have an error, it's probably because your fraction's in the wrong spot. So just like the last problem that we just did, if I plug in cosine inverse, oops, didn't press the second hard enough. Nope, wrong button, of 1 over 1.6, I end up getting an angle measure. And we need to do the positive and negative version of that because we're talking about cosine. And at 0 point, we're running to 2 decimal places, so 90. So one of those answers is 0.9, which is between 0 and 2 pi. And let's just make sure I don't make the mistake. Again, I'm going to do negative. I'm going to go copy and paste this and add 2 pi to that. And I'm also going to write down the work that I did. I'm going to do negative 0.9 plus 2 pi, which I'm writing down the rounded value, but in the calculator, I'm using the copy paste version of it and get 5.39. And those are our 2 angles. And you can go about checking to make sure that those angles actually give you a ratio of about 1.6 for secant. And you do that by doing 1 over cosine of 0.9, which is pretty close. All right, what about cotangent? Well, cotangent inverse, the reciprocal of that is tangent inverse, but we need to reciprocate the ratio, which is 1 over the 3.421. So that's going to give me, if I type that into the calculator, an angle measure, 3.421. And we end up getting, rounded to 2 decimal places, 0.28. Which, sweet, that's one answer. But how do I get other answers? Well, for tangent, the rule is we add pi to that because tangents, this is a positive ratio, so in quadrants 1 and 3, 0.28 is in quadrant 1. To get to quadrant 3, we add a half circle, so plus pi. And we end up getting rounded to 2 decimal places, 3.43. And there's your 2 answers. Ooh, it's fine with that oval looking one on the last one, but I usually like to box up my answers with a non-askew rectangle. Sine inverse. This is where a lot of people have problems. So if I were to type this into the calculator, I would get sine inverse of negative 0.247. And we get a negative angle measure. Rounded to 2 decimal places, 0.25. Well, there is a way to get this to be positive by adding 2 pi to it, but I'm not going to do that yet because that's just going to cause us more work. The rule for sine inverse is that we have an angle, the calculator value, and we have its supplement. The supplement is pi minus whatever the calculator gave you. This is going to give us one of the answers that we need. So if I do the supplement of that angle, and notice that I copied and pasted the exact thing that the calculator gave you, and it's always pi minus. I have a lot of people that try to do plus pi, and it sometimes works, but don't do it. Just do the supplement, 180 minus or pi minus, whatever you're given, which is 3.39, which is an angle between 0 and 2 pi. How do I get another angle for this? Well, you don't do the supplement of that. You do the coterminal of the negative angle that you have. The coterminal is adding a full circle to it to make the angle positive. So I'm going to go up here, copy and paste the angle that the calculator gave me, and find the coterminal angle by adding 2 pi to it. So 6.03. And those are 2 angles. And again, you can go in and check to make sure that sine of 6.03 is pretty close to, a little higher, but or a little more negative than negative 2.47, but pretty close. Okay. So again, check your answers. Make sure that you're following the rules for the inverse trig functions. All right. So even and odd function should be something that you talked about in Algebra 2. Possibly in our on-level Algebra 2, but definitely in our advanced Algebra 2 here at Anderson, you have talked about even and odd functions. So even functions is when you plug in a value of x that's the opposite sign, and you end up getting the same y value. So no matter if you plug in a positive or negative number into an even function, it comes out the same output. Like, for example, x squared. X squared's an even function because you think like, oh yeah, the exponent's even. But that's not by definition what an even function is. So for example, x squared, if you plug in negative 3 in parentheses squared is positive 9. So is when you plug in positive 3. That is the reason why x squared is an even function. So most, even powers are an even function, but it's only if it's like that. Something else that's helpful about even functions is that they're symmetric along the y-axis. So this was something just a few years ago that I ended up figuring out about even functions, because if you had an x squared function that shifted left or right, it's no longer an even function. Just because the exponent's even doesn't make it an even function. It's if it's symmetric along the y-axis. If you plug in a positive or negative version of a number, it always gives you the same output. Like for example, cosine. If you do cosine of 60 degrees, well, think about your unit circle. 60 degrees, that point that's way up there, it's only going a short distance to the right of 1/2. What about negative 60 degrees? Well, that's going, to the further down point, but it's still only going over to the right 1/2. So cosine is actually an even function. If cosine is an even function, then secant is also an even function, which are the only two even trig functions that we have. And then here's that extra graphs are reflected along over the y-axis thing that I wrote down earlier. Well, what's the opposite of an even function? An odd function. An odd function happens if you plug in a negative input, it negates your output. What does that mean? Well, let's think about x cubed. And again, x cubed is not an odd function because it's an odd degree, but because of it being a reflection over the origin, or it has a symmetry along the origin. That means you fold it along the x-axis and the y-axis. So if you kind of visualize that cubic function, fold it along the x and then the y, and you get that same piece of the graph. But numerically, what happens? Well, if you plug in 2 into x cubed, you get 2 times 2 times 2, which is 8. Sorry for pulling up the color palette there. But what happens if you plug in negative 2? It's the same, 2, but just negative. Well, negative 2 times negative 2 times negative 2 is negative 8. So it's the same number, just the opposite sign. So if you plug in a positive or the opposite sign into an odd function, you end up negating the output. Like, for example, sine of 30 degrees. Sine of 30 degrees is that kind of short point, that first point if you're going counterclockwise on the unit circle, which is only going up a tiny little bit of 1/2. Negative 30 degrees is going the opposite direction, which is again that first point to the going clockwise on the unit circle, and you end up going just a little bit down, which is negative 1/2. So that makes sine an odd function. Well, if sine is an odd function, cosecant is an odd function. Well, what about tangent and cotangent? Well, like I said earlier, cosine and secant are the only even functions. So that means sine, cosecant, tangent, and cotangent are odd functions. Oops. So how can we use this here? Well, let's look at these examples. So we're taking sine of a negative angle. We're using t as theta instead of drawing the theta symbol, so t is theta. T is an angle. So they told us that sine of a negative t is 2/3. Well, if we're changing the sign of our input, we're changing the sign of our output since sine is an odd function. So since the output is 2/3 and it's positive, we change the sign and get negative 2/3. Well, then cosecant of the positive t is just the reciprocal of sine of positive t, so you just get negative 3/2. What about secant? Well, secant is an even function. Cosine and secant are the only even functions. Well, to go from secant to cosine, we're just doing the reciprocal, so 5/8. Well, if I'm changing the input, the sign of the input from positive to negative inside of an even function, what does it do to our output? Nothing. So it stays 5/8. What about cotangent? Well, cotangent's an odd function. If you change the sign of your input, you change the sign of your output. So it went from positive 1/5 to negative 1/5. But what about tangent of negative t? Well, tangent of negative t would be the reciprocal of cotangent of negative t, so -5. Make that 5 a little bit more like 5, and that's that. Then, if you look at the next couple of problems, we have pi minus t and t plus pi. So what does pi minus t remind you of? Well, the supplement. So I want you to kind of think of the supplement. Where is the supplement of an angle? Well, if you're talking about like an angle of 30 degrees, the supplement is 150 degrees. So you change it from quadrant 1 to quadrant 3. But if I ask you to do the supplement 150, then you kind of do the same thing. You're going from quadrant 3 to quadrant 1. So this kind of goes both ways. But what if I give you an angle in quadrant, oops, I put 3, 2. Sorry. So 150 is in quadrant 2. Another one of my mistakes, like always. I'm trying to think ahead, and I apologize for that. So supplements kind of go from quadrant 1 to quadrant 2, and then quadrant 2 to quadrant 1. But if we're in quadrant 3, that would end up going to quadrant 4. Like if I ask you, what's the supplement of 210 degrees? Well, it ends up being negative 30 degrees, which is in quadrant 4, and vice versa. If I give you an angle in quadrant 4, does that. So what it kind of does is that it reflects it over the y-axis, very similar to even functions. But what about this other one that says we're adding pi to our theta? Our angle is being added pi. Well, let's kind of think about if I do this correctly this time. What if we ask you, hey, here's an angle in quadrant 1, add pi to it, add a half circle to it. Where does it go? This one actually goes to quadrant 3. And if I give you an angle in quadrant 3, if I ask you to add a half circle to it, where does it go? To quadrant 1. And then the same thing happens if I give you an angle in quadrant 2. If I give you an angle in quadrant 2 and I ask you to add a half circle to that, where does it end up going? Quadrant 4, and vice versa. So what these are doing is that they're changing the quadrants. Pi minus t kind of reflects over the y-axis. T plus pi is kind of adding a half circle. So you kind of have to visualize this, and depending on which trig function it is, kind of use ASTC to kind of help you remember which one's which. So let's say cosine of t has a ratio of 1/5. So some angle for cosine gives you 1/5. Well, the easiest way to think about this is, let's just say theta is in quadrant 1. If cosine goes from quadrant 1 and we're doing pi minus t, which moves it to quadrant 2, what happens to our cosine? Well, cosine in quadrant 1 goes to the right, so that's positive. Cosine in quadrant 2 goes to the left, so you end up ending up with a negative ratio. And that's only because it's cosine. What about cosine of t plus pi? Well, again, if we kind of think about this very basic, let's just say our angle's in quadrant 1. T plus pi is adding a half circle, so it goes from quadrant 1 to quadrant 3. What sign do we get if we're talking about cosine in quadrant 3? Well, quadrant 3 is going to the left, so negative 1/5. But that doesn't happen for every single trig function. It all depends. Like, for example, sine of t. Again, let's say that since sine of t is a positive ratio, let's just make it easy and go to quadrant 1. Sine of pi minus t says that pi minus t, you're changing your angle over the y-axis. So if we're going to be in quadrant 1, it changes to quadrant 2. Well, sine in quadrant 2 goes up, so it stays positive. So they don't always change sign. It all depends on the trig function. And this goes for tangent, cotangent, secant, cosecant. It's all depending on what's going on. Well, what about sine of t plus pi, where you're taking your angle and adding a half circle to it? So if we keep it basic and say with quadrant 1, adding a half circle moves it to quadrant 3, which what happens with sine if it goes to quadrant 3? Well, it goes down. So it's negative 2/3. Might be a little confusing. Just practice it, understand the assignment, check your answers, ask questions, tutorials. But that's that.